All right, so today we're going to continue with chapter 8. And if you remember chapter 8, we're talking about sampling distributions. So last class we talked about sampling distributions for numerical data. Today we're going to talk about sampling distributions for categorical data. So we've kind of put categorical data on the back burner for several chapters. I did mention that in the beginning of the semester. I told you that we were going to kind of set that aside and just focus on the numerical data, and we did. Now we're going to bring categorical data back in, and you're going to see how we're going to relate what we did last class for sampling distributions for numerical data, and we're going to relate it to the categorical data today. So first I need to give you some information and background and definitions, and then we're going to get into that distribution. So first of all, we're going to be working with something new, and it's called proportions. And a proportion is just a number considered in comparative relation to a whole. So it's a fraction, right? So it's a number out of a total number. So here we're going to focus on what we call successes. And I want you to know a success doesn't mean it's right. So it's not a right or wrong. Success does not mean majority. It just means that's what we're studying, that's what we're interested in, and we're wondering how many individuals answer yes or fit in that category of what we're studying. Okay? So some new notation for us. I'm going to start with P, and that this is a lowercase p, not an uppercase P. P is considered the population proportion. Okay, so this is similar to mu, where mu is the average, right? For the population, P is our population value, and it's for the proportion. And we're going to get into a little bit more of what these are, and hopefully we'll get a good understanding as we move forward. The next value I want to show for the notation is P hat. So this is just P hat. And P hat is the sample proportion. I want you to know that P hat is a statistic, right? So remember last class we discussed what a statistic is again. We talked about it in the beginning of the semester, but we brought it up again. And that's just a value from my sample. And that was my X bar that we discussed last class. In this class, we're going to focus on this P hat. It's my proportion from my sample. So this is a statistic. So today, we're going to take a look at the sampling distribution for this P hat value. Okay. So this is called the sampling distribution. Of the sample proportions. Which is P hat. I'm going to start running out of room here. Okay, so let's take a look at what we can expect from the sampling distribution of my p-hats. And we'll get into p-hat a little bit more. So p-hat, like I mentioned, is a statistic, meaning it's from the sample. The value of p-hat changes from sample to sample. So if we're studying maybe how many people out of the class have blue eyes, right? It's not that I'm looking at a number. It's not numerical. I'm going to say, do you have blue eyes? And you're going to answer yes or no, right? So either you fit in the category of blue eyes or you don't. And that's going to be my p-hat. So my p-hat is when I take a sample. So I might be taking a sample of 10 students at a time. And I want to know how many out of those 10 students have blue eyes. So the p-hat is the proportion of the number of people out of that sample of 10 students that have blue eyes. And I'm going to do it over and over again. So each sample will have a different p-hat, right? Because I'm going to have a different number of people answering yes to the question that they have blue eyes. So, so since it changes from sample to sample, it is a random variable. And since it's a random variable, it has a probability distribution. Okay. I'm going to show you how to calculate p-hat. P-hat is equal to x divided by n. X stands for the number of individuals in the sample with a specified characteristic. That's what X stands for. So that's the number of individuals who answered yes, that they do have the blue eyes. And then N is the denominator, and N is just my sample size. So that doesn't change, right? All throughout the whole semester, N is always the sample size. Same when we go into Stat 2. Okay, so p-hat is a good estimate for our population proportion. So our sample proportion estimates the population proportion. Which is P. I like to keep that in mind. It's similar to numerical, where X bar is an estimate for mu. Same idea there, okay? P-hat is the proportion of successes. Remember, that's what we're looking at, successes in the sample. And I just want to make a note down here. We might see something like zeros and ones come up, meaning instead of like yeses and nos, okay? So a success would be a 1, and a failure would be a 0. So we might see that. A success is a yes, a failure would be a no. So I just want you to be familiar. You're going to see different things out there. It all comes back to the same thing, right? Number of successes divided by the total number in our sample size. So right now, we're not actually going to calculate this value, but we need to know what it stands for and what it represents. So when we're ready, we have it, okay? Let's talk about the distribution, how to describe this distribution like we did last class with sample means. So this gives us a lot of information about it, but I want to know how to describe this distribution, okay? So we're going to do the same thing we did last class. I'm describing the sampling distribution. And I'm going to shorten it to just p hat. So that's what it is. I'm going to describe the sampling distribution of my sample proportion, which is p hat. Okay. All right, so just like before, and like we always do, when we describe a distribution, we want to talk about the shape, the center, and the spread of that distribution. We can visualize it then we can move forward and do things and calculate maybe probabilities or percentiles, right? Because that's what we're focusing on right now. So first, I want to talk about the shape of that distribution. All we know right now is normal, so that's what we're looking for. We're looking to prove that this distribution is going to be normally distributed, right? Bell-shaped, symmetric. So when we're doing this, we're looking for a certain quantity. So this is if n times p times 1 minus p is greater than or equal to 10, then we can go ahead and say that the shape is normal. So with the numerical data, I had 3 different ways, right, to say it was normal. Not here. With proportions, so p hat, I only have this way. So I just want to remind you, n is my sample size. I know I just wrote it on this slide before. And p is the population proportion. Just like to remind you here what that is. So you can't just say, well, n has to be a certain value and p has to be 25% or something. I can't just say that because they rely on one another, right? So depending on what the population proportion is, my n will change to make sure that the whole value is greater than or equal to 10. So that's why I can't just have like set values. It's the combination here of these. And of course, just like last class, as n increases here, my sampling distribution will become more normally distributed. Okay, so same as last class, n's always, as n gets larger, it's always a better and more accurate representation of the population when I have a bigger n, a bigger sample size. Okay, so it's always better to have n larger. Just not always feasible. Okay, so let's talk about the center of this distribution. The center here is going to be very similar to last class. So 2 weeks ago, we said, oh, the center is the mean, right, mu. Last class, we talked about that the center was the mean again of all of those x bars. The same idea here, it's the mean of all of my p hats. So if you think about it, I'm going to get proportions here. So for every sample, I'm going to get either, you can view it as a fraction, or I like to view it as a decimal. And you're going to take all of those and average them up to get the center, right? The typical value for p hat. We're not actually going to go through all the work of that. If you have all the distinct samples of size n, this value will come right back down to the population proportion. So the average of all the proportions for the samples will come back to the population proportion. It's the same concept as last class with numerical data. It's just now we have something new, which is proportions. So P here, I'm just going to make a note that this is the population proportion. You know, it gets a little confusing. We're talking about population, proportion, sample proportion. We've got a lot of P's going on here, right? But like I said, we'll get used to it because we're going to work with these the rest of the semester. We're going to continue with this stuff. The last thing we want to talk about when we describe a distribution is the shape. The spread. So with the spread of the distribution, very similar to last class, I'm looking at standard error again. So I'm just going to write out all the different notations. So it's the standard deviation of my p hats. So same thing as last class, but we don't call it the standard deviation of p-hats, we just call it the standard error. So right here, this is the standard error of the sample proportions. All this means is it's the standard error of my p-hats. I'm going to put that right here. So remember last class I mentioned I put like X bar here, and now I'm going to put p-hat because I have something new. So I don't want to just call it standard error. I want to know it's standard error of p-hat. I want to just kind of distinguish between the two from last class to this class. And this has a specific formula, just like last class did. It's the square root of p times 1 minus p divided by n. Now keep in mind these are lowercase p, so these represent the population proportion. And n represents the sample size. So same as up here above. And just to make a note, because I know we've been working with probabilities a lot and we see that P, we think of probability, but that's a capital P. This is a lowercase p. It is hard to distinguish on something like this. When I'm writing it like this is what I mean, okay? Same idea as last class here. Look at where n is located. It's in the denominator of my fraction, right, for my spread. If we're just looking at the calculation, if n is a really large number, it makes this entire fraction really small, right? So if n's really large, it's making my standard error or my spread of my curve very small. What happens when that's small? It makes the curve more narrow, right? It makes these little p-hats come down closer to p. And that's just based on my sample size. That goes back to that a larger sample is better. It gives me a better idea, more accurate information about the population, and it does. And we can see it here with the calculation or when we just think about it, that it does make sense, that a bigger sample is better, yep. So, you know, and we saw that last class as well. What I want to mention is what P and 1 minus P stand for. We already talked about P's, population proportion, but I mean out of successes and failures. So I'm just going to make like a little note down here at the bottom that P is the proportion or the probability of successes, and 1 minus P is the proportion or probability of failures. So remember, if you're talking about success or failure, it's a yes or no, right? You have one way or another. There's no in between. So if P is the proportion of successes of the people that answered yes, or individuals that fit in a category, then 1 minus P would just be the opposite, right? Those are my failures. I just want to point that out. I mean, it makes sense once I say it, but some people don't really maybe think of it in that way. So I want you to think of it in that way. That's how we're going to describe the distribution. This might come back up because we're going to do an example here in just a minute after I show you some notation. So the notation I want to show you is just like the notation I keep showing you every class right now. It's not that I ask you to write this for me often, but I give it to you. You might see it on your homework, and I'd like you to be familiar with it. I don't want you to be lost if you see this. So the notation here is P hat follows a normal probability model with a center at P and a spread at the square root of P times 1 minus P divided by N if N times P times 1 minus P is greater than or equal to 10. Right, so that's just our notation, right? Sometimes in the team assignments, they give you this, right? And that tells you that it follows a normal model, meaning the shape is symmetric, gives you the center of the distribution in the spread. And then we can go forward, we can calculate probabilities, we can calculate percentiles, and we could do things with this. So it's just my notation. I want to show it to you so you have it. Let's take a look at an example, just similar to last class, where we're going to describe the distribution and we're going to calculate something using that example. So today's example, I have information from the National Center for Education Statistics. And they say that the proportion of U.S. high school students who took a stats class in high school is 0.11. And I'm just going to put it here as 11%. I may say 11%, but how I'm going to view it is as 0.11. And how I'm going to write it all the time is in a decimal form, 0.11. Okay. A random sample of 150, I abbreviate, high school students is taken. So there's my sample information. Let's describe the distribution of p hat, and let's find the probability that the sample proportion is greater than 0.15. Okay, so it's like a lot, right? It's like a lot to take in. So just like I did last class, I'm going to label what I have and what I'm going to need. So I don't have to keep going back and reading this and wasting my time. I want to just pick it out really quickly and move forward, right? So that's always something I like to do. You don't have to do it. It's just I like to do that because I like to move forward if I can. So I'm going to just start reading. National Center for Education, the proportion, right there. You see that word proportion? I'm going to underline it. Because when I see that word proportion, I need to start thinking about categorical data right away. We don't talk about proportions for means, right? For numerical data. So proportion, it should make me think categorical data right away. P hats, right? And it says U.S. high school students took a stats class is 0.11 or 11%. So this value right here is my lowercase p. Okay. Now it says a random sample of 150 students. This is my n, right? That's my sample size is n, which is 150. Now it says describe the sampling distribution of p hat. Right there. So now we've learned two sampling distributions. Last class was x bar. This class is p hat. So when I see sampling distribution, I should make a note. Okay, that means I'm going to be using standard error for my spread, right? Then once I see what it's about proportions, so it's p hat. So even if it didn't say p hat down here, I know it's proportions up here, so that would make that automatically p hat. Okay? So that's the information I'm going to pick out. You could see it's less information than what I get for my numerical, right? Because for numerical, I need the mean, I need the standard deviation, then I need the sample size. All right, so let's take a look at how we're going to describe this distribution and find that probability. So to describe the distribution, that's the first step here. Remember, just like last class, I'm going to use that information. I'm going to use the calculations about that distribution to find my probability. I'm going to describe that distribution. And it's the distribution of p hat, right? So the first one is the shape. So from the shape, I want to say that it's normal. I just need to prove it. So remember we discussed that it's normal if n times p times 1 minus p is greater than or equal to 10. So n is 150. We picked that out up here. Not that you can see it, so it's not on my screen. Right here, 150. So I have 150 times, now P, I'm going to just use parentheses to separate them because I think it's easier. P right here is 11% or 0.11. So 0.11 times 1 minus P, so 1 minus 0.11 is greater than or equal to 10. Now, if you're showing me this work, this is really all I need to see, and you can just kind of check it off. You don't have to actually show me your calculation, but it's fine if you want to, and a lot of people do. So when I multiply all these, it's 14.685. I don't need to see all the in-between steps. I just really need to see that second line. I don't even really need to see the first line, although it is nice to know what you're using. The second line is important because I like to see what values you're plugging in, right? So I don't really want to just see the first line, then a check mark. It's nice to know that's what you're using. I want to actually see what you're plugging in. So when I say show your work on this one, this is what I want. Line 2 here, okay? All right, so 14 is greater than or equal to 10, so my shape can be assumed normal. So I can say that this distribution follows a normal probability model. So that's good. That means I can go forward with the second part of the question, which is finding the probability. So first I want to continue with my describe the distribution. So I want to find the center. Remember, the center is just the mean of all of those p hats, which comes back down to the population proportion, which is 11% or 0.11. I'm going to always write it as a decimal. And when we look at the curve, I'm going to use those all as decimals, not percentages. So the third part is the spread. And now this is the one I have a little calculation. So this is the standard error of my p hats. So my calculation here, so I just have the p times the 1 minus p divided by n all under the square root. Now I'm going to plug into this. P is 0.11, 1 minus 0.11. Yes, you can write 0.89 there. That works as well. I get the picture, okay? I just like to see what you're plugging in, basically, for these p values, because they change as we move forward with the class. So here I get a spread of 0.0255. Just like last class, when I had the spread, I kept it 4 decimal places. The reason for that is it just gives me more accurate probability when I calculate probability. So I don't round to 2 decimal places here yet. I wait and I do the 2 decimal places on the probability. If I don't specify, it's fine. Like on an exam or something, I calculate using all different values. So you get credit, even if you round it early. Okay. So this is my distribution. I could visualize this. It's bell-shaped. It has a center of 0.11, right? Half's below, half is above. And I have a spread of 0.02. So on my second one here, I didn't write it out in notation, right? I just said, find the probability that the sample proportion is greater than 0.15. So I want to write it in notation. I have the words, I want to write it in notation. Find the probability is capital P, that the sample proportion, there's p hat, is greater than 0.15. So if you just go right along, you can read it and write it into the notation. This notation doesn't help me too much for my calculator or Minitab, like what I'm going to plug in. So I'm going to draw my picture and I'm going to write it in a different way. You don't have to do this. This is something I like you guys to do. I like you to be familiar with this. You don't have to do this, but you will notice I do this often. So the center of my curve here is 0.11. Now I'm going to put 0.15 because that's my interest, right? And I want to know the probability around that value where it's greater than, really. And if I look, 0.11 is my center, 0.0255, that is my spread. So 0.15 is actually kind of far from 0.11 in that respect to that spread. I'm going to put it up here. It doesn't really matter where you put it. You don't even have to look at the spread. You could just put 0.15 on there and then you do your shading because it's greater than, so it's everything to the right. This gives you an idea of what you're doing. It gives you that visual. And it takes me just 1 second. From here, I'm going to write my probability in a different way. I'm looking at the probability that 0.15 is less than a p-hat, is less than, and of course, same as usual, infinity. Okay, so that stuff doesn't change, the infinities. I know and you know they only go to a certain value. My density function does not know. Since I'm calculating a probability based on my normal curve, I'm still going to use the normal CDF in both my calculator and Minitab. And what I plug in is the same idea. My lower bound, 0.15. My upper bound, I'm going to use 10,000. That's a really large number compared to 0.15 or 0.11, so I'm good with that. And my center, which is 0.11. Remember, we always use decimals in our calculators in Minitab, not percentages. And my spread, here I pointed the wrong thing, 0.0255. So right here is why I keep it 4 decimal places, because if I rounded to 0.03, it might not be as good of an answer. It's gonna be really close, but when I plug this all in here, I'm going to get an answer of 0.0584, or we can write this in percentage, 5.84%. Okay, and that's, you can see where I rounded 2 decimal places. I leave it 4 here in a decimal, and then I just round it to 2 for my percentage. Now, what does this mean? This is the area, right? So the area under the curve here is 0.0584 or 5.84%, right, of the curve is shaded in here. So that's what we're talking about. And sorry, I'm choking here. So 5.84%, it's a probability rate. It's the probability that I'm going to randomly select a sample proportion of those 150 students that 15% of them took stats or more, took stats in high school, okay? So this is where it gets a little tricky. I'm talking about a probability or a percentage of a percentage, right? So I'm saying it's 15% or 0.15. That's a percentage. That's what proportions are, right? You can write it as a percentage. You can view it as a percentage, talk about it as a percentage. So that's where it gets a little tricky, a percentage of a percentage. It's just that it's the probability. So the probability is 5.8% of them, of those samples, okay, of 150 students, 15% of them or more took stats in high school. So don't get overwhelmed with that just yet, because like I mentioned, we're going to talk about this the whole semester. The rest of the semester, we're going to continue with this. We have plenty of time to get that understanding. So don't get overwhelmed with it that maybe it's a little difficult today, and that's okay.
Professor.
Yeah.